So here is another question on properties of electromagnetic waves. So it is given that light with an energy flux of 18 watt per centimeter square falls on a non-reflecting surface at normal incidence. If the surface has an area of 20 centimeters square, find the average force exerted on the surface during a 30-minute time span. Okay, so here it has been asked to find the average force or the force exerted by electromagnetic wave. So here we know that force is equal to mass into acceleration. Okay, Newton's second law. So here ma, we can write it in this form. M is mass, a is acceleration. We can then write it as m into v, velocity by time, speed by time, velocity by time, whatever. Okay, this, which is equal to mv by t, which is then equal to how much? P by t, where P is momentum and T is time. Okay, this much. Now then we have to find out the momentum of light, or which is in this case is the electromagnetic wave. So here it has been given the energy flux. The energy flux that is given how much? 18 watt per centimeter square. So if we have to determine the total energy, okay, the total energy, let's say capital U, that will be equal to this energy flux, watt per centimeter square, okay, centimeter square, multiplied with the area, which is equal to 20 centimeters square, then the time converted to seconds, that is 30 minutes into 60 seconds. So this will be equal to the total energy, which is coming around 6.48 into 10 to the power 5 joules. So why I calculated this total energy? Because total energy is related with momentum. If you remember, in the property of electromagnetic wave, we studied that momentum of an electromagnetic wave, P, is equal to energy of electromagnetic wave and its speed divided by speed. So U by C. Okay, so here that is equal to 6.48 into 10 to the power 5 by 3 into 10 to the power 8 meter per second. This much joule, this much meter per second. So that momentum, it is coming around 2.16 into 10 to the power minus 3 kg per second. This much. This is the momentum. Now here we just derived previously that the average force or the force exerted, that is equal to momentum by time. So here the average force exerted, that will be equal to momentum by time, which is equal to 2.16 into 10 to the power minus 3 by time, which is equal to 30 minutes. 30 minutes time span into second, converted into second, 30 into 60, that is equal to, it is coming around 1.2 into 10 to the power minus 6 Newton, this much. So this is the average force exerted. Okay, so here first we use the simple formula of force, which is force is equal to mass into acceleration. From that we convert it into this form, which is momentum by time. Then we had to calculate the value of momentum for the electromagnetic wave. For that we calculated the total energy. Momentum is equal to energy by speed of the wave. From here we calculated the momentum, and then we went back to the initial formula, which is asked to determine the force, which is equal to momentum by time, and here we got the result, all based on properties of electromagnetic waves. Okay, so here is another question on properties of electromagnetic waves. So it is given that a plane electromagnetic wave is propagating in the x direction, has a wavelength of 6 millimeters. The electric field is in the y direction, and its maximum magnitude or amplitude is 33 volt per meter. Write suitable equations for electric and magnetic fields as a function of x and t, that is position and time. Okay, so first let us be clear about what the equations will be. Okay, so basic representation. So the basic representation is, for that, here it is given that we have an electromagnetic wave. Let us first draw the axis. Okay, x, y and z. The electromagnetic wave is propagating along the x-axis or the positive x-axis. The electric field is in the y direction. Okay, so the amplitude variations will be along the y direction, like this. So obviously the amplitude variations will be represented with EYT. So that will be equal to the peak magnitude E0 cos omega t minus x by c. Okay, like this. How we got at this expression, I have already derived in one of the previous videos, okay, where we got how we derived this expression from cos omega t minus kx, that. So omega is equal to 2 by f, and here E0 is equal to the maximum magnitude, that is equal to 33 volt per meter. So obviously the magnetic field variations will be along the z-axis, because electric and magnetic field, they are in mutually perpendicular directions and also perpendicular to the direction of propagation of wave. So direction of propagation of waves along x, electric field is along y, so obviously magnetic field will be along the z-axis. They will be in the same phase, the same frequency, so magnetic field will be along z-axis, represented by b subscript zt equal to b0 cos omega into t minus x by c. Here x is the propagation direction. So here E0 is equal to this much, so b0 will be equal to E0 by c, which is equal to 33 by 3 into 10 to the power 8, which is equal to 1 into 10 to the power minus 7, approximately this much. 1.1 into 10 to the power minus 7. Yes. Yeah, 1.1. Okay, this much. And then this is the B0 value, and then we have been given the wavelength lambda is equal to 6 millimeter. So we have to determine the angular frequency. So we know is equal to 6 into 10 to the power minus 3 meters. So we know that lambda by time period, wavelength by time period, that is equal to c. That implies lambda is equal to ct. Okay, that implies we can write it as or here lambda f is equal to c. We can write it in this way, this will be better. Lambda f is equal to c because 1 by t, reciprocal of time period, is equal to frequency. Lambda f is equal to c, that implies f is equal to c by lambda. F is equal to c by lambda. Then omega, angular frequency, omega is equal to 2 pi f, which is equal to 2 pi c by lambda. So we'll substitute the values, 2 pi into 3 into 10 to the power 8 by lambda, which is equal to 6 into 10 to the power minus 3 meter. It is coming around how much? It is coming around pi into 10 to the power 11 radian per second. So we have got omega, we have got B0, we have got E0. Now we can write the equations, the electric and magnetic field equations. So first is the electric field equation, EY as a function of t and x. So it is equal to E0, which is equal to 33 volt per meter, cos pi into 10 to the power 11, which is equal to omega into t minus x by c. Okay, c is equal to 3 into 10 to the power 8. I am not writing that, just I am writing it as c. And the magnetic field equation, Bz t, that is equal to 1.1 into 10 to the power minus 7, 1.1 into 10 to the power minus 7 cos, again same angular frequency, pi into 10 to the power 11 t minus x by c. Okay, so it will be better if we write it as xt, ey xt. Okay, ey xt and bz xt, because it is a function of both position and time. Okay, so let us just remove that. Okay, simply we'll write as ey and bz. Okay, this would be better. Okay, as a function of both x and t, position and time. Okay, this. So these are the two representation of electric field and magnetic field here. Okay.